So you are welcome for today. Today we'll be looking at linear regression. The last time we discussed correlation. Somehow they are related. So the term regression is a historical anomaly. It was coined by Francis Galton in the 19th century to describe a biological phenomenon. The phenomenon was that the height of descendants of tall ancestors tend to regress down towards, please mute, please. The phenomenon was that the height of descendants of tall ancestors tend to regress down towards a normal average, a phenomenon known as regression towards the mean. It simply means that the average value of y is a function of x. That is, it changes with x. What do you mean by regression back to the mean? If parents are tall, the children will be tall, but not as tall as the parent. If parents are short, very short, the children also will be short, but not as short as the parent. So, Parul, please move. Parul, move, please. So, if parents are extremely tall,
I think your network is
can you hear
breaking or
me?
something, or is it just me? Is it from myself?
Is it breaking? Can you hear me? Can Motar, can you hear me?
Yes, we can hear you, sir.
Maybe it's your own network. So when parents are tall, very tall, the children will be tall, so they're not as tall as the tall parent. So if parents are very short, also the children will be short, but not as short as the children. So what it means that when some people are extremely tall or short, they are far from it, because average in the society will not be as tall as those people or as short as those people. So their own children, what they will do is that they will try to move towards the average. That's what we call regressions towards the mean. The word regression sounds like go back in some ways. The term has appeared in early writings since the late 30s, and is derived from the Latin term regressus, which means a return. It is used in different fields with different meaning, but in any case, it is always referred to as action of regressing. In philosophy, regression is used to indicate the inverse logical procedure with respect to that of the normal apodictics, that demonstrable or indisputable truth, in which we proceed from general to the particular. Whereas in reality, in regression, we go back from particular to general, effect to cause, condition to the condition. When we say particular to general, you are trying to give a general model from a particular data you give, you have, effect to cause. In regression, you are looking at, what are those causes of those things? It's those causes of those things you are looking at. Like, for example, what are the factor determinant of high blood pressure, something like that, or hypertension? So these causes, you are moving from effect to the causes. So hypertension, what are those factors that determine hypertension? So effect is the hypertension, the cause are those factors. Condition to the condition. Conditioned, that is, maybe the hypertension is a condition to the condition, what causes it. In statistics, the term regression has an ancient origin and a very special meaning. The man who coined this term was certain Francis Galton, a geneticist. I've told you, A lot of people that developed statistics were genetics, they were biologists, especially genetics. In 1889, he published an article in which he demonstrated how every characteristic of an individual is inherited by their offspring, but on an average to a lesser degree. And you see now, for example, children with tall parents are also tall, but on an average, their height will be comparatively less than that of their parents. This phenomenon, also graphically described, is called regression. Since then, the term has lived on to define statistical techniques that analyze relationships between two or more variables. In Gattin's world, this corresponded to the concept of regression towards mediocrity, hence the name of the statistical analysis technique. Timeline of scientific discovery. In late 18th, Franklin Gattin, influenced by cousin Charles Darwin. So he was cousin to Charles Darwin. They were cousins. So Gattin begins nature-nurture debate. Early 19th, Gregor Mendel, genetics work with field realized as important. 1920s, quantitative genetics developed. 1950, DNA discovered by Watson and Crick. Early 20s, human genome sequence. So Sir Francis Gattin coined eugenics and nature versus nurture. The Gattin universal regression law was confirmed by Carl Pearson, Gattin's student. So Pearson, that first one described Pearson chi-square, that described chi-square, and coined the word standard deviation. I also discovered this Pearson correlation coefficient for the student to Gattin. He collected more than 1,000 heights of members of family group. He found that average height of the children from a group of short parents was greater than the average height of their father's group. Average height of the children from a group of tall father was lower than the average height of their parents' group. That is, the height of the tall and short children were regressing towards the average height of all people. I have a way of predicting, so it's actually a way, not a way. A way of predicting, so regression is a way of predicting an outcome variable from one predictor variable. That's simple regression, or several predictor variables. That's multiple regression. So we can predict any data using the following general equation. Outcome, that's what you are predicting, is equal to model plus error. So mind you, when we talk about regression here, today we are talking about linear regression. But when we talk generally, we are talking about general regression. So when the outcome is continuous, it's linear regression. When the outcome is categorical, it's logistic regression. So forget the exposure variable can be one. That is simple regression. If it is linear regression, it is simple linear regression. If it's logistic regression, simple logistic regression. When the exposure are many, so it will become multiple regression. If it's linear regression, multiple linear regression. If it is logistic regression, multiple logistic regression. So multiple regression, either multiple linear regression or multiple logistic regression, are referred to as multivariable analysis. So we can predict any data using the following general formula. Outcome is equal to model dot error. The simplest description, so we want to first talk about the origin of this regression model equation of a straight line. So we borrow from mathematics, which is equation of a straight line. If you remember, y is equal to mc plus mx plus c rather. So the simplest description of a relationship between two continuous variables in a straight line, that's the equation of a straight line. The shape and the position of a straight line is defined by intercept and slope. Intercept is where the line crosses the y-axis. Or you can say that's the value of y when x is 0. Slope is the gradient. How slopey, how slanty. Slantiness is the slope. So if it's very slopey, you know the slope is so slanty, almost close to vertical, that's steepy. The slope will be higher in quantity. But if it's almost flat, the slope will be lower. But it's more than that. It depends on the direction of the slope, whether it's negative slope or positive. So we are going to look at it. So the intercept is the value of y when x is 0. The slope is the amount y increases or decreases for each unit increase or decrease in x. That is, the amount y changes with unit change in x. That is the slope. Look at this line, look at the equation, look at the graph. The slope, look at the y is equal to mx plus c. The slope is that, so change, if you look at organic slope, change in y over change in x. So that's how I draw this vertical and horizontal. This vertical is the change in y, then horizontal is change in x. So change in y over change in x is the slope. You remember your further ones here, the y, the x. Now, let's look at the slope of graph, because you can have, how do you consider slope? Slope, look at it, when it is positive, it goes up from right, it go up from slanty, from left to right. That's positive slope. If it goes down from left to right, negative slope. So if you see when it is horizontal, it's not slope, it's not sloping. The slope is 0. When it is vertical, the slope is not defined. No, when something is vertical, it's vertical. But when it's tilted, it's sloping. Now, so let's also look at both combination of slope and intercept. So because you're going to see that the slope gives you the shape, whether it's slant from right to left, up, or from left to right, up, or from left to right, down. That's the shape. But the location in geometric space is the intercept. You can see this 4 graphs. So a line, the first one is a line with positive slope and a negative intercept. So if you look at it now, if you know when you draw y, mind you, y is the dependent variable, x is the independent variable. You know, unlike correlation, two variables you are looking at the degree of association, there's no dependent, there's no independent in correlation. But in regression, there is dependent, there is independent. So y is dependent, which is your outcome. The x is the independent. So x can be one, only one independent variable. In simple regression, it can be more than one, it can be 2, 3, 4, as many as possible. That's multiple regression. So let's just start with, okay, let's assume it's 1, 1, 1. So you see this first graph now, where the slope, you see x horizontal, y vertical. You know where the cross is the origin of the graph, 0. So from that origin to the right side for x is positive. To the left side is negative value of x. From that origin up, is the y, positive y. Down is negative y. That's the direction. So now you see that first graph now, the slope is positive in the sense that it goes up from the left to right, but the intercept where it crosses the y-axis is see on the positive side. So that's why we have positive slope, positive intercept. The second one on the right side is still slope upward. It's still positive slope. But the intercept where the graph cross y-axis is on the negative side of y. So this is positive slope, negative intercept. The number 3, you see the slope goes down, it's negative slope. But it crosses y-axis at the positive direction, that is positive intercept. So negative slope, positive intercept. The last one is still negative slope, but the intercept is negative where it crosses y-axis. Can you see now? The first one, positive slope, positive intercept. The second one, positive slope, negative intercept. The third one, negative slope, positive intercept. The last one, negative slope, negative intercept. Can you see now? That's because those are the two parameters that describe this equation of a straight line. So this equation of a straight line, when you apply it into statistics, it's just the same thing. It's only that you decide to change the what you call them. So instead of calling y and x, this is the same. But instead of that, intercept is a, call it constant, is a, instead of saying is c. Why? This one, mx, that m, which is the slope, is b. So this b now is what we call regression coefficient. That's the slope, regression coefficient. And that is the dy dx we thought change in the outcome variable per unit change in the exposure variable. B, by that change in b over change in y rather over change in x. B slope of the graph is the regression coefficient. A is constant, the value of y dependent variable when x independent variable is 0. Each value is equal to a plus by. So each value of y is, so if you want to predict y, that's the origin of that model I told you now. Want to predict y, which is the outcome, is the model, which is a plus by and bs or bs plus a. This is the regression equation. And you see y is equal to a plus bs. That's the simple one on simple regression equation. So when simple linear regression, the way it is written, b is equal to bo. What just means that even that a, you want to call a, the value of y when x is equal to 0. That's why they put b0. That's value of x when value of y when x is equal to 0. When there's no the x has no value or x does not change, doesn't mean that y will not change. The reason is very simple. Very simple. When you say you are looking at relationship between two variables, height and weight, it's not only if the height, see which one determine which. Weight is determined by what? Let's talk about age and height of a child or weight of a child. Age and weight. The outcome variable is the weight. The exposure variable is the age. So if, well, let's look at the, even when the age has not changed much, doesn't mean that weight will not change. It's not really age that determines somebody's weight. So when you remove the effect of age, which is x, doesn't mean that b will not have some change. So that is why that b0 is the constant a. Then byxy. So this one now, the by1 is the regression coefficient for that exposure X. So that first one is simple regression. So when you have two variables, up to as many n variables, 20 or whatever, so multiple linear regression will be y is equal to b0 plus by(xy) plus b2x2 plus b3x3 plus b3x3 plus b4x4 plus up to bnxn, depending on number of exposure variables. Of course, this is what we call multiple linear regression. Now, that's what is written. You will see something that has been introduced. Now, apart from that, those constant and the change you observe in each of the exposure variables, there's something error. So, if you look at it the first time in the beginning, I said that you want to build a model. See, outcome is equal to model plus error. So this is the model. But you, of course, you are trying to predict y. The model may not 100% predict y. For example, if you are using simple linear regression now, one variable, you know that you have a lot of variables that may influence y. You just one variable, you see that it may be just a small part of y, the x that one variable will predict. That is the model. The other that it cannot predict, that is the error. But if you have many exposure variables to form the model, so the error will be smaller because those many exposure variables will predict many parts of y. So it may not predict everything, but the more you have the exposure variable that predict y, the less the error. The closer within the value, the prediction to the original value. So the difference from the prediction and the real value is the error. Does it make sense? It's just like you remember if people want to build church, they build the model. They do the model, their cathedral, maybe their permanent site or whatever they want to do, or campground or whatever. They build it, they do the model. And made that a picture or in this thing. They come and show in the church, they play it. They stimulate people. This is the work of God, what God wants to build. So people will begin to bring money, so that thing will come to reality. But by the time they finish building, if you compare what they build from what they show you, it's not the same. So the difference is the error. That's just a simple way of explaining. Now, this regression model, this is the way it looks, in actual sense. In the equation of a straight, this is a line. That line is a line of regression, which is the model you build. But because the model will not 100% predict the data. So now, this dot, the y is the dependent variable, which is the vertical. X is the exposure variable, which is horizontal. So that model, you see the regression line that go up like that. And then it can go down, depend on the slope relationship. But let's say it goes up like this, slanting. You will see that the line, that is, for each value of y, the corresponding value of x, that's what they use to plot the dot. If you see how many dots you see, if you see 20 dots now, it's 20 value of y and x for each person. They use to where they meet along the scale of y and x, that's where the dot is. So you will see that if, let's say, the model perfectly predicted, all this line will be, all the dots will be on that line. But because the model does not perfectly predict it, for each value now, let me see. Okay, I will still talk about that. So how do we even draw the model, get the model? If you plot graph, you collect your data, for y and x, you plot the graph. You have what you call scatter graph. Look at the example I just showed you now. So 2 ways you can plot the graph. You can do it manually. You can have each of them just have ruler and draw a line you think is closest to each all the value. Just draw a line across. But that type of thing, you agree with me. If you give to different people, 30 or 10 people, to draw line on this thing, they will draw different line manually. So it's a crude way. The other way that is more refined, that is more scientific, is to use method of least square. What do you mean by this method of least square? So I want to, what it means is that method of least square, when they are scattered like that, the line that we pass through, that you now look at the distance of each value dot from the line. You draw the distance, just like what they did here. You draw the distance of each value from the line. When you square it, it gives you smallest value. Why do you need to square? If you remember, you need to square. Look at this one now. You draw some line. The value of the line for the dot that are above the line, they are positive. The one dot that are below the line, the difference is negative. If you try to, remember when we were talking about the correlation, we talked about when we were demonstrating covariance. I demonstrated it now. You have the line, each value, they differ from the line. How do they differ? The one that are below, that's negative. The one that are above, positive. If you try to add negative and positive together, because if the line is actually the line that pass through, that is the best line. When you try to add together, give you 0. But because they are positive and negative. That's why intelligent people, what they do, remember when we were discussing how you do variance. So you square it. When you square it, you remove negativity. So when you square all the distance away from the line, imagine somebody you draw your line, you do it, you square it, all the distance you had together, another person. Let's say we have 5 people that draw different line. So if they come with different value, when they square the difference, the deviation from that something, remember that deviation is with the error. I talked to you for each of the value now. The value for maybe this number 3 or number 4 now here. The value your model predicted is the value on the line where that thing joined the line. But the real value you are seeing is the value where the dot is. But the value predicted by the model for each on the line. So the difference is the error. So error can be positive if what model predicted is lower than the real value, or the error can be negative if what model predicted is above the real value. So when you square, let's say about 3 or 5 people you draw different line, and you square the difference. The one that gives you the smallest value is the one that maximizes the distance between all of them. We can say closest to the all of them, because that is what we call least square. That's what they call it, method of least square. When you square the difference, it gives you the smallest value you can get. That's the closest. That will be the best line. They also call it line of best fit. For you to get line of best fit, the best method is method of least square. Don't know if you understand me now. Line of best fit, method of least square. Now, there is another, before we do it here, I think, is it that I went to run something before I demonstrated? So maybe we should run it. Okay, let's see. Let me re-explain, because this is where, so when you draw the line, after you have drawn the line now, use method of least square. So you may want to see this line, which is the model. how does it assessing the goodness of it? You want to assess how fit is this line. There are two ways to assess the goodness of fit. So I said most model, the mean, the most basic model. The two ways are using R square and F ratio. We talk about both of them, R square and F ratio. Now, the most basic model is the mean. How? You remember when you calculate the mean, you want to calculate the standard deviation, you say deviation is observed minus model. Model is the X bar. Observed is what is the X? X minus S bar. You know, we now square it because we know that if we had all the S minus S bar, which is deviation, it will give you some are 0, some are minus, some are positive. It will give you 0. So that's why we usually square. So sigma observed minus a model square, which is X minus S bar square. So mean is the model in this situation. So mean is the most basic, is the crudest model. Is a crude model in the sense that imagine now if you have a school and you have a maybe nursing and primary school and you want to do inter-sport, you now say your friend went to UK, say, hey, please help me buy jersey and inter-sport vest and shorts for my student, houseware for my student. So when the person got there, you know, call you. What is they will say, what's the age you are looking at? They will not call your friend will not call you, oh, what is the age or average, what's the age of your student? So what do you think? The proprietor or proprietors will call their principal, head teacher. What is the age I will look at? What is the average age? They will look for average age most of the time. The average age of our student is around 7 years. When they say 7 years, you will see that is the average. A lot of people are less than 7, a lot of people are more than 7. So this person can go and buy just something for mostly for 7 years today. And by that they bring it, it will be too big for some, yes, some it will fit some. It will be too big for some, it will be too tight for some. So that is, so predicting with, what do I call it? Mean is crude, that's the crudest model. Now, for you to now assess the goodness of it, how good is this your model? The best you have on ground is the mean, even though it's the crudest. The best you have is the mean. Look at the way we do it. Look at the first graph here. You will see that, mind you, the vertical axis is the Y, the horizontal axis is the X. So you know that the outcome you are predicting is the Y, is Y. So the mean of that Y is this horizontal line. So if you try to predict, you use mean as the model, look at each value and what is their difference from the mean. That would be the error in predicting each of them. Then look at this second graph. This is if you are to use regression line to predict as the model, to predict the value. Look at it. So which line is closest to those values? You can unmute and answer. Is a workshop. Unmute and answer me. Which of the between the mean and the regression line, which one is closest to this value? To those dots.
Line, sir.
Yeah, regression line. Thank you. So it is obvious that the regression line is better than the mean. But you still want to assess this, how good is this your regression line? And there's no other way to compare except the one, the mean. So the only thing you cannot do is that, okay, how better is this regression line than the mean? Yes, I mean, we know that regression line is better than the mean. They are how better, because if you have regression line that's far, far better than the mean, it's better than the regression line that's a little bit better than the mean. Can you see that? So you want to use the regression line. So now, if you remember, when we were talking about how to calculate variance the other time, you remember that this is what I just showed you now. You say, what is the deviation? X minus F, that error, this error is this deviation. So this, if you square each of them, it gives you total. So this mean, which is the cruded model, is the one that gives us the total variability we can observe in the data set. Is the mean. So we know that the variability is not because they are far. So the variability here now is when you square the distance, the error, the distance from the mean, you square it, and if you now calculate you divide it by the degree of freedom, it gives you the variance. So the same thing, if you look at SS uses, this is SS using the differences between the observed data and the mean value. Sum of square, that SS sum of square, you remember, square you sum it. The sum of square for the mean is the total sum of square. Sum of square. So, I told you something also, that regression and ANOVA is the same. You remember when we say sum of square, you X minus grand mean, we now say give us total sum of square in ANOVA, is the same thing here. So this sum of square total is when you remove the mean from each value and square it, give you sum of square total. The same thing as the sum of square grand mean total for ANOVA. Now, if you look at this one now for the regression model, the regression and the error, we have already said that the difference between each value and the regression is the error. So when you square is sum of square, you can call it sum of square error. Well, regression. Residual, rather. This is residual. The error is the residual that it won't remain for it to completely predict sum of square residual. And this sum of square residual is the one that corresponds with the sum of square within in the ANOVA. I told you sum of square within, between, and total sum of square. So sum of square within is the one that corresponds in the ANOVA, is the one that corresponds with sum of square residual in regression. Sum of square total here is the same thing as sum of square total also in ANOVA. Now, if you remember in ANOVA, there's what we call sum of square between, which is actually the model for that ANOVA. So that sum of square between now is now the difference between these two. We know that, yes, the total variability we can have is the one given by the mean, which is sum of square total. Then the variability, the regression model is able to give us is the sum of square regression. So the difference, what is the improvement? What is the improvement the regression model have upon the mean is when you overlap both of them, you now minus it. Can you see now? When you overlap the graph now, so the difference now will be sum of square model uses the difference between the mean value of y and the regression line. Can you see? So the difference, so when you remove sum of square residual from sum of square total, it gives you the sum of square model, which is the improvement the model, this model have. Can you see now? That's how to do the. So let's look at it now. The R square now is the sum of square model, this one here, divided by sum of square total. That is, we want to know what proportion of the variability Because sum of square model is what the model, regression model, is able to explain for us. So now, we will now what proportion of the total variability this regression line is able to sum of square model divided by the total sum of square. You can express as percentage. That's what we call R square, or you call it determination, coefficient of determination. By the time we run it, you will be surprised that R square, which is, the R is the Pearson correlation we did on Saturday. When you square the Pearson correlation, it gives you the same thing. So that's why they call it R square. This R square is the same as sum of square model over sum of square total. What it tells you is that what proportion of the variability that the model is able to. Another way of saying it, what proportion of the variability in outcome variable, the exposure variable, which is the model X, is able to explain. Coefficient of determination. So the second thing is the F ratio. The F ratio is the same F ratio we calculate in ANOVA. If you remember, we use sum of square, mean square between over mean square within. Mean square between is the mean square model here. This sum of square model, if you calculate you divide it by the degree of freedom, it gives us the mean square model. If you calculate this one, the other one also, the one for residual, by the degree of freedom, it gives us mean square residual. Mean square model over mean square residual, it gives you the F ratio. Just like mean square between divided by mean square within in ANOVA give you the F ratio. It's the same F ratio. So that is why we know for this one, especially that F ratio, we know that regression and ANOVA, they are the same. So let's look at our data set. So this, I don't want to bother with you because the same thing we did, if you remember, is the same data set I used for correlation. I put here height and pulmonary death space, and the formula for okay, how do we derive it? Just like the way we derive the formula for correlation for covariance. Look at it here also. The same thing. Variance of X is this. Variance of Y is this. Covariance, we demonstrated that time. Now, covariance of X and Y. Then consider the following. Change in X is the variance of X. Change in Y is the variance of Y. Change in Y due to change in X is the covariance of X and Y. So the regression coefficient B is change in Y per unit change in X. So that covariance, so if you now therefore covariance of X and Y divided by variance of X. Can you see now? Covariance of X and Y divided by variance of X. If you do, it gives you formula for regression coefficient B. Simple. You don't need to, it's just a logic, but you don't need to cram that. And from there, you can, if you know the value of X and Y, you'll be able to know, you can actually calculate the average, the mean value of X and Y. When you put it, you'll be able to calculate the Y and B. Now, let's look at well, solving is not, solving with hand does not even make anything. So look at it, you just solve with your hand. Let's just go straight to our data. So somebody is going to read for us that particular data. That pulmonary dead space. Who is reading? Who is sharing? So the people here, as now, can you share?
Yes, sir.
Okay, share. Pulmonary dead space. So I didn't see your friend Mercy today. Okay, maybe I didn't allow you to share. Let me. You can share now.
Sorry, sir, I didn't see it. Let me go and re-download it.
Ah, okay, don't worry. Who has it? Samira. Samira. You have to unmute if you are talking.
Yes, sir.
Can you
Good evening,
share?
sir.
Yes, good evening.
Sir, I have issues with my phone. That was why I couldn't even join last week.
You never share. You always have. What of Farouk? Mukhtar. Mukhtar, Farouk.
Yes, sir.
Can you share?
Okay, sir. Let me share.
Me, I've opened it to. I just want you to, because that's the only way you can learn this thing. If you do it, you run yourself. So I've opened it. So that when you open and share, open the data set. Yeah, thank you. We're looking for it.
This one, right, sir?
Is a pulmonary dead space.
Height and pulmonary dead space.
Height and pulmonary. Yes, I click on that height and pulmonary dead. Click here. Open. Okay, share again. Yeah, log out.
Yeah, I didn't know it had height. I've seen mine.
Okay. Height and pulmonary dead space. Yes. So let's do it percent by percent. You remember, let's first of all do correlation so that we don't do the regression, because we are going back to see that arrow square. So go to analyze. Correlate, bivariate. Move both height and pulmonary dead space here, both of them. Yes, by default, you say piercing correlation. That's all we need. Click OK. So stop sharing and share the result with us.
Can you see the result?
Yes, you can see. You will see that the correlation is 0.846, right? That's all they want us to see, 0.846. So go to analyze. You can go to analyze from here also, from the result window. Go to analyze. Go to regression. After correlation, you say linear. Go to linear. We are doing linear. Linear regression. Is the number 2 now? Linear regression. So move what is your dependent variable? Which one leads to which? So your dependent variable is pulmonary dead space. It's height that determines pulmonary dead space, not the value. So pulmonary dead space, move it. Then independent variable is height. Move height there. So click OK. You will see, you will see your table. Yes, okay. You see the table. We say the first one variable enter. You see model one height, because that's the only variable we enter as this. It's variable with pulmonary dead space. Look at the second table. You see R square. You know, I told you of R square, one of the way you use to measure the goodness of feet. R square. You see R 0.4846. That's correlation. Can you see R is correlation? You know, we have done correlation for the two of them, and we see 0.846, the same thing. Then the square 0.846 times 0.846 gives you 0.716. If you express it as percentage, that's 71.6%. That is the R square. So that is the what we call coefficient of determination. That's the percentage change in Y that's accounted for by the percentage change in change in X. Percentage change in Y accounted for by change in X. That is the coefficient of determination. And you see now is by, if you put your phone now, just say 0.846 times 0.846 give you 0.716. So you will see also the, look at it. You can see regression. Can you see the model table now? You will see the similarity between this table and ANOVA. You see under you have regression model, residual, and total. In ANOVA, where you see regression, that is between. Where you see residual is within. Then this total is total also. Square, sum of square, can you see? This sum of square 5607 is the one that corresponds with sum of square between in ANOVA. This 2221.502 is the one that corresponds with sum of square within. The other one is sum of square between. This is within. Then the total sum of square. And the total sum of square, when you add the two together. And here, the degree of freedom is 1. Because there are two things in the equation, that a b0 plus bx. You know, only one, there's constant plus that bx. Those are the two entities. So these two entities now, that's the, you now divide by, you remove 1 from it, it gives you degree of freedom 1. For the residual, you see the degree of freedom is 13. If you go and check, the number of this thing there is, what do I call it? Is 14 entity. No, you know there are 15 people. So the degree of freedom 30 plus the total degree of freedom is 14. Look at the mean square. If you divide this 5607.40 divide by 1, it still gives you the same thing. When you divide this one 2221.502 divided by 30, give you this. F is this 5507.432 over 117.885. It gives you the F. This is significant. So exactly like, so if you want to prove it, you want us to prove it now. What I'm saying, I want somebody to, it may not be, let Asmau share that Viagra. data, the one we use for our ANOVA. So you can stop sharing. Asma, share the Viagra data. We'll run ANOVA and run regression with that data because I've already
Sorry, which
created
data,
the
sir?
Viagra. You see it there now. You were not around for that ANOVA, right? Can you see it?
I've seen it, sir.
Okay. Great. So we will first of all do ANOVA with that dose and libido. We now run regression with libido and those two dummies. So first of all, go to analyze. Go to compare means. No, compare means. Compare means. One way ANOVA. So move dependent is libido. Move it now. What happened? Your computer is slow. Okay. So yes, dose is factor. Move dose under factor. Yeah. So just click OK. So don't worry, don't go and let's run before we go there. Run the second one, go to analyze. Before we go and show the result, go to analyze. Go to regression, linear. Dependent is libido. Independent are low dose and high dose. You know, there are three categories: placebo, low dose, high dose. But we use placebo as the index, the one for, what do I call it? Reference. So you compare low dose with placebo, high dose with placebo. That's what we use it. That's the two dummy we created. Can you see now? So go to OK. So go and share your distance. Share your window, result window. On yeah. Make it bigger. It's not. Thank you. So you will see. Scroll up small before the regression. Let's see the ANOVA. Can you see? Don't scroll too much now. It's just the ANOVA. Scroll up. You just want to so to see so that the still move us small so that ANOVA will be at the edge so that we can see some of those other ones. Move up so that the ANOVA will just be at the top. Wow. Okay, don't worry. It's okay. It's okay. It's okay. You will see. Can you see? This is ANOVA. You see sum of square. Can you see the value? 20.133. between group 20.123, within group 23.6, total 43.733. Oh yeah, scroll to the ANOVA table, the second table of ANOVA, of regression rather, regression. Go scroll down. Would I just put it side by side? Scroll down now, smile. Scroll down. Is that your computer is not responding or what? Asma, can you hear me? If you are muted, we cannot hear you. Hello? Share again. It's like it's out of the. Can you see? Let me share now. It's like it's having network problem. Let me look for that data set and share it.
Sorry, sir, my network went out. Do I still have to share?
And share now. We saw that your network went out. Share the result. Why is it taking time? Asma, maybe I should share my own. Oh. Can you people see my own? Please talk, please. Unmute and talk.
Yes, sir, we can see
Yes,
it.
yes, we can
So
see.
let me quickly run this thing. Let me quickly run from my side. So analyze, compare means, one way, ANOVA, libido, factor. So let me, I don't know if what you are seeing the result.
So is it analysis? Is it ANOVA you used to run regression analysis on this program? Didn't I just start from something?
You didn't start for maybe what no, maybe we did ANOVA where you are here. I told you the last I said ANOVA and regression they are the same. I want to demonstrate it with the data we used to run ANOVA. That's why I just did. So I've run the
Oh,
ANOVA now. I want to run the regression. I will want to compare the two so that you see the two. That's what I'm doing.
okay.
Regression, linear. So I don't know if you are seeing. Can you see the result? Are you seeing it? Or I should share. Can you see? Please, I
Yes,
Yes,
want
sir.
I'm
when
seeing
I'm
it. I
asking
don't know.
question, you unmute and answer me. Because so sometimes you see the ANOVA. you see the ANOVA, look at the ANOVA table. You see what I was demonstrating. You see sum of square between 21.133 within group 23.6 total 43.733. Look at the degree of freedom 2, 4, 2, 12, 14. Look at the mean square. Look at the F test. So let's scroll down now. Look at the result of regression. Can you see similar something? Can you see this regression? This regression is the, look at sum of square. Sum of square regression is the same thing as sum of square between, which is 20.133. The sum of square residual here is the same thing as within, which is 23.600, the total sum of square. So I've already told you the sum of square, the regression here is the one, the improvement you made, when you remove the regression line, the residual from the mean, the variation by they give you the sum of square model, which I demonstrated to you, and it corresponds with the sum of square between in ANOVA. The residual here, which is the sum of square residual in the regression, is the same thing as sum of square within in ANOVA. The total sum of square here is the same as total sum of square there. If you look at it, the degree of freedom is the same. Look at the mean square. Can you see? Look at F test. F is 5.119. Its p-value is 0.025. It's the same thing with what you have in that ANOVA. Look at it. Is it not the same thing? Look at F, 5.119. P-value is 0.025. So that's why ANOVA and regression are the same. That's why when you run a regression, you see a table ANOVA. It's the same ANOVA analysis of the variance. Can you see now? So that's just the demo. And I've already demonstrated, told you the R square. This R square is square of correlation coefficient in there. So now the table, there's this one. Okay, let me run the other one. Anyway, let me know there is one table we have now. Okay, yes, the one what's the name? Let me run that one also. The one Mokhtar, is it Mokhtar? Yes, that run. Let me run it here. That pulmonary dead space. Let me stop sharing this one and share that one. Pulmonary dead space. Should be this one. The pulmonary dead space. Let me just run the regression straight. I hope it's not correlation. I want to analyze regression linear. Pulmonary dead space is dependent. This one is independent. The height. So let me share the output. Can you see? So now we have explained the ANOVA for that one. The one I've done explain is the coefficient table. Look at coefficient table. This coefficient table, we see beta here. This is what we call the beta, the coefficient, the constant under the B. You know, we have already said that both of them, even the what we call A and B. A is the constant, which is the intercept. B is the regression coefficient. But in Lie equation, both of them are coefficient. But that constant is B0. That is the first one you see here. constant. Then you have the one for that bx1. Just a minute, just 1 minute. So now, so the constant here is minus 82.4485. While the B, which is the regression coefficient, is 1.033. So now this is there's the other time I showed the T, how you can use T to know if it's significant or not after you have calculated the regression, but actually those ones are not so important. They are not so important. Now let's talk about how I have another data which I didn't share with you, because this one not just have one exposure, one outcome. I have another data that has some outcome that exposure that are more than one. We peak expiratory flow rate. Well, I don't usually use that one as primary data for use that actually is lengthy because it's about over 300 or 600 sample size. But I actually use just something you can use hand to calculate, so that you know how to calculate it with hand, then how to run it. That's why I don't usually use anyone that has large sample size. But that one has like I will share it now. I will run that data. I will do multiple regression. You will see what happens, where we have many variables involved. So it's not that one. Let me go and check it first. Peak expiratory flow rate, okay. So this is what I've shared now. This one, if you look at the data set, you have age, weight, height, peak expiratory flow rate. So if you breathe in deeply and now breathe out the maximum you can breathe, so they usually measure it with a spirometer. So they use instrument to measure peak expiratory flow rate after you have your deep breath. Now breathe, expire the air. So they measure the peak expiratory flow rate. So they compare, they look at weight, age, weight, even sex, though I didn't put sex in this data set. Then we have age, weight, and height. Because in the study I analyzed for that person, those are the major factors: height, then weight, age, even before sex. So those are the factors that are major factors. So if you are the peak expiratory flow rate is the outcome measure, while the exposure are age, weight, and height. Look at what happened. Regression, linear. The peak expiratory flow rate is independent. So height, that's the most important. Weight, age. This is multiple regression now.
I was going to ask you that you said linear. I was wondering. Okay.
It's linear now. It's linear regression. It's
And
linear.
there are more than one.
More
There are
than
more than
what?
one independent.
That's
Variables.
multiple. That's multiple linear. It's not. If it is only one independent variable, that's simple linear regression. If it is logistic regression, simple logistic regression. And this is multiple linear regression. Yes. Let me share the outcome. So you can see, if you look at the first, you see that what are the variables involved? We put in age, height, weight. The dependent variable is peak expiratory flow rate. And you can see the model R square is 62.5%. So actually, if you do it one by one, the percentage will not be up to that. But if you do it one by one, height is the one that gives the highest percentage, then followed by weight, and before each. Look at the ANOVA and look at the coefficient. This is where I'm going. The coefficient, you see, the constant is minus 731.158. For height, the coefficient is 6.828. For weight, 0.01. For age, 2.34. Now, for interpretation of each of them now, for a unit change in height, the peak expiratory flow rate will change by 6.828. For a unit change in weight, the peak expiratory flow rate will change by, will reduce, if it's given minus, will reduce by 0.01. For for any, will decrease, yeah. For a unit change in age, the peak expiratory flow will change by 2.36. Can you see now? So now, in a reason, when we analyze it, we don't usually put all of them together at once. We do it one by one as simple regression first. For example, now, if I want to do it, I first of all start, if I start linear regression, linear. If I start, I want to start with height first. So even if we start with age, whichever way, let's begin to see the R square. And that's what matters most, R square. So when we do for height alone, can you see? Height alone, can you see? Only height. Can you see? The R square is 62.3. What it's telling me is that 62.3%, 0.623. But if you express a percentage, it's 62.3% of peak expiratory flow rate is accounted for by change in height. So if you do it, repeat the same, let's use weight now. Remove height. Weight. So look at it. Okay, sorry. Let me scroll very well. Look at the percentage. 27.9. Can you see now? That is what is telling you that if the weight per unit, for a unit change in weight, this one changed by 27.9. Yeah, I was wondering. The coefficient is not negative here, it's positive. And let's do, if you look at it now, 27.9%. For height is higher, 62.3. So let's do for age now. For age, you remove weight, put age. Oh, yes. Age, look at it. The value is 28.8. So from the value, you know that height is more important, is the most important, followed by age, followed by weight. So now we now begin to do what we call, if we do for many, they will give you different value. So we will now say, if we want to do the regression, want to see is there any improvement, because height is the number one factor. So that's why we do multiple. We now say, okay, what we do is we run it, we say regression linear. We now put, okay, let's put, I think height number one, followed by age. The age is more important than weight there. And that's okay. So we now want to see what is the, can you see age and height? Age and height. Yeah, age and height. You see the 62 point, age alone, height alone 62.5 into 2.3%. With height, it's just 0.2 increase. So if you, let's now add the way we did, we now add weight to read. What improvement? Or if we had height, it give you, it increased by 0. Let's remove height and put not height. Let's remove age now and put weight. Let's see, is there any better increase? After we have put height, instead of putting age, we want to put weight. That's the way we do stepwise regression. So, what am I doing? Linear regression. So, instead of age, let's put weight to join height. Let's see if it's going to improve. 62.4. So that shows that the weight, age is better than the height in weight in that situation. So what we want to do now, that is why you now put if, let's now add, first of all add, let's put weight, height, age, and weight now to see the improvement. So this is it doesn't matter once you even put them together. Age. So the three together, what does it give us? It gives us 62 points. So that shows that in real sense, weight does not even have any extra usefulness. So from here now, it shows that it's the height and the age, not the weight. Does it make sense? Any question? So for each of them, you can interpret their regression coefficient. Any question? So this regression issue, the more you do, the more you read about it, and the more you get to understand it. A little bit complex. Something that once you conceptualize it, you can do it. Any question?
Okay. When you do the multiple linear regression and like this height, age, and weight, you want to know the one that has the most effect on
The peak explosive flow rate.
Won't he give you a table where you can compare it at a glance?
Which table?
Or maybe I didn't catch that. You see a table
No,
where you
it's
can
you that way. If I show you, no, it's you. You cannot get. You have to do it stepwise. You have one by one. When we run the analysis, let me show you the way we show you. I have the table of the result. Word document. This one. I'm trying to share that. Yeah, this. So initially, can you see the table I'm showing? You see? Okay, this one is correlation. So the same thing, can you see now? School type, private. Look at different things I use there to screen. Simple regression, R square for each of them, F ratio, P value. You see that age 18.9% on its own. For that something, sex, either male, female, because we discovered that male have higher, averagely higher respiratory. So you now use female as a reference. How many times a male is more than the female? That's 9.7.9. That if you're a male, so as a male, what's the percentage? If you want to know for female, we make female, we code female 1, male 0. But because we know that male is higher than the female, that's why you use this one. Weight 22.1, height 26.9. Can you see now? BMI 1.7. This is where we screen them. This is what we call simple linear regression. Each of them now, or when you say simple linear regression, each of them you do each of them one by one, to really know the effect. So we now start with this one, that this height, since it's the one that has the best. You now choose the one that follow weight to see what improvement does it make. You put, for the fact that age does not give value as weight, doesn't mean it doesn't give more improvement. So by the time we put age, it can even improve better than weight. We now put weight, age will be the next. Sex, that's how we do to build the model. You understand me now? So look at when we now build it now. We selected his height, age. Can you see now? Height, age, sex, weight. Those are the important ones. I continue. So can you see now? For each of them, step 1, only height. Can you see the regression coefficient for the height? So here we have the R square, F ratio, P value here. So step 2, we've added age. So of course, both height and age have their regression coefficient. It will be changing. Yes, I'm now. Because this regression coefficient is what per unit increase in height, what is the unit change in the quick explosive volume, per unit increase in age, what is the change in the quick explosive volume. That's what you are seeing here. So this is the R. So, but that is not that unit something that make them important, but the R square, the total change you can get by the combination of them. You understand me now? So the next one, we had hex. So when we had X now, we now say, okay, look at the 36.1. We now have weight 38.4. So what is telling you now? Height, age, sex, and weight account for 38.4% of change in peak explosive volume. So any other thing you don't know, maybe each of them, they are too plenty. Each of them small. Some of them may not even be part of what you collect data, and may be accounted for the remaining 60-something%. That is the way it is done. So we now build the model. We now use equation. We even have what do I call it? Nomogram. It plots a chart for male and female by looking at your age, height, and weight. We can predict your peak explosive volume. We did that. Any question? So the one thing with statistics is the more you do, the more you know. The more you do, you read, know, do, read. That is the way to learn. Thank you. Any question? Any other question?